Hi, welcome to the first video of the real analysis course. In this video, we are going to learn about sets. We first outline the topics that we are going to cover in this video. We will first look into the definition and some examples of sets. Then we will move on to set operations such as union, intersection, complement of a set, and symmetric difference. Then we will move on to some properties of these set operations such as commutativity, associativity, distributive laws, and then De Morgan's laws. Let's get started. Here's the definition. A set is a collection of well-defined objects. The phrase well-defined means that there is no ambiguity. If I give you something, you will be able to tell definitively whether it belongs to the given set or collection or not. So, here are some examples of sets. Set can be denoted by a capital letter A, which is given in this case by 1, 2, 3, 4. So it's a set containing these four numbers 1, 2, 3, 4. Here are some more examples of sets. Cool. Now here are some notations and conventions used in the literature for sets. Sets are generally denoted using capital alphabets such as A, B, C, D, etc. And the elements of sets are denoted using small alphabets such as A, B, C, etc. The symbol X belongs to A means that X is an element of A, and this is how it is denoted. X belongs to A. And then you have B subset A, which means that every element of set B is also an element of set A. Then you have equality of two sets, which is the same thing as saying A is a subset of B and B is a subset of A. Very well. So let's get started with the next thing, set operations, union of two sets. Now given two sets A and B, their union is the set of all the elements that are in A or in B. So they can lie in any one of A or B. Here's an example. Let A be the set given by 1, 2, 3, 4, B be the set 2, 4, 6, 8, 10. Then their union is given by all the elements of A. So 1, 2, 3, 4, all of them will come. 1, 2, 3, 4, and then 2 and 4 are already taken in account, so we don't have to write them. So we just write the remaining elements 6, 8, 10. There you go. This is the union of two sets. Let's also see this through Venn diagram. Venn diagram is a pictorial representation of this situation. Suppose you have set A, B, then the union is represented using these shaded area, which covers all A and B. Alright, moving on. Next we have intersection of two sets. Again, suppose we have two sets A and B, their intersection is given by all those elements X, such that X belongs to A and X belongs to B. Here, and is the key word here. It has to belong to both of them. As an example, consider again set A given by 1, 2, 3, 4, and then B 2, 4, 6, 8, 10. Their intersection is given by this. Now 1 is not in the intersection, 2 is in the intersection. It belongs to both. 3 is not in the intersection, but 4 is. So 4 comes here, and this is the intersection. With Venn diagram, it is given as follows. Say you have A, you have set B, then the intersection is represented by this common area that is shaded in yellow. There you go. Moving on, we have complement of a set. Now, when we talk about complement of a set, there is something called universal set, which is a bigger set that contains all the sets under consideration. With universal set U, the complement of any set A is given as follows. It is all those elements in the universal set that do not belong to A. That's it. As an example, suppose the universal set you have is the set of natural numbers, and your set A is the set of even natural numbers. Then its complement is all the numbers that are not even, which is the same as the set of odd numbers. So that is the complement of set A. Again, through Venn diagram, it becomes clear to visualize. Suppose you have set A inside a universal set U, then its complement is all the elements that lie outside of set A. Alright, moving on. There's another important concept called relative complement. So given two sets A, B, A minus B is defined as all the elements of A that do not belong to B. Now this is called relative complement of B with respect to A. Here's an example. Again, consider set A given by 1, 2, 3, 4 and B given by 2, 4, 6, 8, 10. Now consider A minus B. Now this gives you all the elements of A that are not in B. 1 is in A, not in B, so it remains. 2 is also in B, so it goes away. 3 is not in B, so it remains. 4 is in B, it goes away. So this is what you get. Through Venn diagram, we can understand it better. Say again, you have A, you have B, then A minus B is given by this area right here, all the elements of A that are not in B. Alright, moving on. The next operation is symmetric difference between two sets. Symmetric difference. Given two sets A, B, the symmetric difference between A and B is given as all those elements that either lie in A or in B but not in both A and B, meaning it shouldn't be a common element. Here's an example. Consider set A given by 1, 2, 3, 4, B 2, 4, 6, 8, 10. Then asymmetric difference B is all those elements of A that are not in B. So that will be 1. 2 is in B, so it will not come. 3 is not in B, so it will come. Now 4 will not come because it's already in B. Now from B, 2, 4 again will not come. But 6, 8, 10, they do not lie in A, so they come in the symmetric difference. This is it. Through Venn diagram, we can see it now. Suppose you have set A and you have set B. Then the symmetric difference is given by all these elements that are in A or B but not in their intersection. And there you go. Cool. Alright, moving on. Let's now look into some properties of these set operations. The first in the list is commutativity. Commutativity means the order in which you perform the given operation. So let's look at union. Now commutativity sees whether A union B is equal to B union A. It's pretty clear that these two quantities are equal. To see, we can just convince ourselves using the Venn diagram. The left hand side is represented by this Venn diagram. And similarly, for the right hand side, if you draw the Venn diagram for set A, B, you get the same thing. You take all the elements of B, unite them with the elements of A, and you get the same thing as left hand side. So union is a commutative operation. Moving on. Similarly, you have intersection. We want to see if A intersection B is equal to B intersection A. Again, with the help of a Venn diagram, we see that the intersection is given by this common area right here. And if you do the same for the right hand side, that is B intersection A, you get the same thing. It is the common area. So both the expressions are equal. So we say that intersection is commutative as well. Alright, let's investigate the next operation. Next operation would be relative complement. And we want to see that given two sets A, B, whether A minus B is equal to B minus A. Again, with the help of Venn diagram, we see that A minus B is given by this area right here. You consider all the elements of A that do not lie in B. What will be B minus A? It will be all the elements of B here that do not lie in the intersection. And we can see that they are not equal. So relative complement is not a commutative operation. Last we have symmetric difference. Given two sets A, B, we want to see if asymmetric difference B is the same as B symmetric difference A. Again, from the Venn diagram, we see that asymmetric difference B is given by this area right here. You leave out the intersection part and consider everything else. And we can see that these two areas are symmetric in B. It doesn't really matter which order you consider. So we can see that this symmetric difference is actually a commutative operation. Now that we have established this, we look into the associativity property of these operations. In associativity property, we first look into the union. We want to see if this expression is actually equal to that expression. Here you have three sets ABC. You want to see that if you take union of A, B first, and then take its union with C, AB first, then it's a union with C. We want to see if it is equal to taking union of B, C first, and then uniting it with the elements of A. Boom, we get both the expressions equal. So that means that associativity is followed by the union operation. We do the same thing for intersection now. Again, for intersection, we consider three sets A, B, C, and we want to see that this left hand expression, whether it is equal to the right hand expression. For the left hand, we perform intersection of A, B first, which is given by this common area here, then take its intersection with C, which is given by this area. For the right hand side, take intersection of B, C first, then its intersection with A, and you get this area right. So both the areas are equal, which means that both the expressions are equal, which means the intersection is associative. Very good. Now let's look at the next one, relative complement. We want to see that if A minus B, then take minus C, whether it is equal to this expression right here. For the left hand side, perform A minus B first, which is given by this area, and then remove C from the shaded area, leaves us with this green area. Now for the right hand side, perform B minus C first, which is given by this yellow area, then subtract this yellow area from A. What you're left with is this particular green area, and it is easy to see that these two areas are not equal, which means that relative complement is not associative. Last, we have the symmetric difference. We want to see if asymmetric difference B first, then symmetric difference C is equal to B symmetric difference C first, and then with A. Left hand side is represented by this area right here, asymmetric difference B. Then you take symmetric difference with C, which is given by this area right here. And for the right hand side, you consider B symmetric difference C first, and then take its symmetric difference with A, which gives you all the elements which are either in yellow or in A, but not in both. Both the areas are same. So it implies that symmetric difference is indeed associative. Alright, moving on. We now look into distributive laws. There are two distributive laws. The first law is as follows. You take A union B intersection C, then A is distributed over B and C as follows. A goes with B, then comes intersection, then A goes with C. Right here. Now to see that these two quantities are equal, we can convince ourselves using the Venn diagram. For the left hand side, perform B intersection C first, then take its union with A, which gives you this entire green area. For the right hand side, you first take union of A with B, which is given by this area. After that, you take union of A with C and observe the intersection. They are equal. Alright, moving on with the next law, the second law. It states that A intersection B union C is equal to A intersection B union A intersection C. Now to see this, consider the following Venn diagram. For the left hand side, consider B union C first, which is given by this area right here. Now take its intersection with A. What you get is this green area. Now for the right hand side, perform A intersection B first, given by this area, and then perform A intersection with C, which is given by this right here, and their union is given by this green area, and both are equal again. At last, we have the last of the set properties known as De Morgan's laws. Just like the previous distribution law, we have two De Morgan's laws. The first law states that if you want to take the complement of A union B, then the complement goes inside for A as well as B. You consider A complement and B complement, and this union gets converted into intersection. Now, for the left hand side, Venn diagram is given as follows. You take A union B, which is given by yellow area right here. Then its complement is given by this green area outside of A union B. And there you go. For the right hand side, you consider complement of A first, which is given by the area outside of A. Then you consider the complement of B, which is given by area outside of B. And their intersection is represented by this green area. Both are equal again. So moving on, we have the second law now. Second law, which states that if you want to take the complement of A intersection B, then the complement again goes to A, B. You consider A complement, B complement, then this intersection gets converted to union right here. To see it with Venn diagram, consider A intersection B, then its complement is given by this area shaded in green outside right here. And for the right hand side, you consider complement of A, which is given by the area outside of A right here. Cool. And then you consider complement of B, which is the area outside of B right here. Shading, shading, and shading gives you this entire region. Now remember, you have to take union, so you want to consider everything that's shaded, and involving everything that's shaded, we make it all in our consideration, and boom, the left hand side is equal to right hand side.